Hello, my name is Hayden, and I'll be starting the demo on the C project deliverable part 2 that I worked on with Tyrone in set A. So to start off, we'll start with the project objectives and scope. The goal of the phase was to improve hospital management system we built in phase 1. Specifically, we focus on scalability, data persistence, and performance. We removed the limitations of fixed size arrays, added a file storage so data isn't lost between sessions, and made the system faster and more robust. This version allows administrators to manage patient records, room assignments, and doctor schedules much more efficiently. Design and implementation details. We kept the system modular with clearly separated functions for each feature. We used a patient struct with a linked list to store data and organize the doctor schedule using 2D array. From the start of the program, it loads existing patient data and doctor schedules through files. Throughout the session, any changes made are kept in memory. Then, before the program exits, everything is saved back to files, so no data is lost. So to start off, dynamic memory allocation. In phase 1, we were limited to a static array of 50 patients that wasn't scalable. So in this phase, we use dynamic memory allocation. We use malloc to create space for each patient. So just Control F, malloc, creating for each patient. And as patients are added, they're linked to a list using pointers. When a patient is discharged, we free the memory to avoid the leaks. And this means the system can handle any number of patients without crashing or slowing down due to memory issues. So for file handling data persistence, previously everything was lost once the program was closed. We fixed that by adding the file handling. So patient records are saved in a binary file called patients.dat, as you can see right here. And we skip the pointer part of the struct when writing to file to avoid issues on the reload. So like on startup, we load all saved patients into linked list automatically. A doctor schedule is saved unloaded from a text file using formatted fscanf and fprintf. We also built backup and restore functions using time-stamped file names. This adds safety in case of file corruption. This way, the system is persistent and reliable across sessions. So for example, in phase 1, when we just did like hospital management system, after we do everything, so like let's say add a new patient, like Hayden, 101, Hayden, then 20, like let's say you have injury and patient's room is like 202. After you exit, it has not been saved because there is no file to save anything from. So when you restart, Hayden's patient is not being saved. It will not load up. Same thing for doctor. But however, since we have the patients.dat and then doctor schedule.txt, we could load up the files. So let's do another demo. As you could see here, patient records loaded successfully. Let's add another doctor this time. So manage, assign a doctor. Then let's say Tyrone is the doctor. Then let's assign another doctor. Let's do like 7 and then 3. Let's say like BAK is the new doctor. And then let's return to see if everything has been initialized. Oh, these are some of the doctors that I put in before I started recording. So there's no issue here. Everything works perfectly. I return to the main menu. Then after you save and exit, data saved exiting, let's rerun this thing again. As you can see, if you go back to manage doctor and then view schedule, it has the same thing as before. And then let's see if we still have the patient. So VO patients, as you can see here, this is the most recent one that I added. As you can see, everything has been loaded. Now I'll hand it off to Tyrone for advanced data structures.
First, let's begin with the foundation of our system. the linked list implementation that revolutionized our patient management capabilities compared to phase 1's fixed arrays. This simple but powerful structure, visible in our patient definition, gives us tremendous flexibility. Each node contains the patient's medical data, plus this essential next pointer that forms the chain. The real magic happens in our add patient function, however. There are several important design decisions worth noting here. First of all, we always initialize the next pointer to null. This prevents dangerous pointers. Second of all, our traversal logic carefully checks for null before following any pointers. This is crucial for avoiding segmentation faults. And third of all, we maintain a global patient list head pointer that always points to the first node in our chain. To see this in action, let's examine the view all patients function. This elegant while loop here keeps on iterating through until it finds a null in the current patient list. So overall, this demonstrates the beauty of our linked list traversal. To put this into detail, we first start at the head, process each node's data, then follow the next pointer until we reach null. Unlike arrays, we don't need to know the total count in advance. The list dynamically reveals the size as we traverse it. Now, moving on to our reporting and analytics, we're going to talk about how we use these features to transform raw data into actionable insights for hospital administrators. First, let's examine two particularly valuable reports, starting with daily admissions tracking and reports patients admitted today function. This implementation solves several real-world problems by using MK-time and Unix timestamps. We automatically handle daylight savings and time zone conversions. This is critical for hospitals that operate 24/7 across time zones. Second, the 86,400 second calculation, which is 24 hours times 60 minutes times 60 seconds, ensures we never miss patients due to clock changes. Third and foremost, we efficiently traverse our linked list just once to gather this data. For room management, our report room usage function takes a different but equally important approach. Here we see a beautiful synergy of data structures as we use our linked list to gather data, then an array for fast room number lookups. The array size of 1,000 accommodates most hospital sizes while using minimal memory. Notice how we skip room 0 since our room numbering starts at 1, as shown here. These small details matter in production systems. And all our reports automatically saved to files is shown in the final part of reports patients admitted today function. As shown here. This dual output, both to screen and file, meets healthcare compliance requirements while providing immediate visibility to staff. Next, we're going to move on to error handling. So in healthcare software, robust error handling isn't just good practice. It's a matter of patient safety. Our system implements multiple defensive layers, starting with comprehensive input validation, as seen in add patient. So here, in this section specifically, we're ensuring the patient's age is within a realistic range, making sure that the age isn't negative or isn't above 125. This is important because it's a matter of the patient's safety in a hospital setting, and our system implements various defensive layers which start with comprehensive input validation as seen or as mentioned earlier. Now, this loop combines 4 critical protections. First of all, the scanf's return value check catches non-numeric input. Second, the buffer flushing prevents infinite loop from leftover characters. And range validation enforces medical reality checks. And lastly, clear error message guides the users to correctly input values. Such as here, we're telling the user there's an invalid input, so enter a valid number. We apply the same rigor to file operations as demonstrated in save patients to file function. Notice that we even check the fclose result. Many systems miss this, but failed flushes can corrupt data. Our backup system provides additional protection. Moving on. Here, the timestamped file names ensure we always have recovery points, while explicit mode quotation WB guarantees binary writing consistently across platforms. Next, I'm going to talk about testing. So, while we didn't implement formal unit tests, the codebase itself demonstrates rigorous validation through built-in safeguards. The restore patience function shows our memory discipline. This careful cleanup prevents memory leaks during critical restore operations. Similarly, our schedule loader includes automatic corruption detection. These patterns create a resilient system that maintains consistency even after unexpected failures, such as corrupted files. Now to conclude, this project demonstrates how fundamental C concepts enable enterprise-grade medical software when implemented with care. The discharge patient function encapsulates our philosophy. From the linked list foundation to the robust reporting features, every component reflects three core principles. First of all, memory safety through careful allocation and free. Second, data integrity via comprehensive validation. Third of all, operational visibility through automated reporting. And overall, the menu function ties everything together, providing controlled access to all features. As shown here. This architecture doesn't just work, it meets the stringent reliability requirements of real healthcare environments, providing that well-designed C remains indispensable for critical systems. And that is all for our process of making this hospital management system, including how we solved errors and validated our system through testing. And that is it for our presentation. Thanks for listening.